guess probably maybe from now until spring break we'll do stuff with Agda, and probably after spring break we'll come back to Haskell. I think it's super fun. And let's see. So I'm on the course website just to show you that there's links here. So this is if you just want to read more about Agda, and there's like a wiki and documentation and stuff. You can go here. But we're going to be using this thing called AgdaPad, which someone amazingly just put it in, like there's just a website where you can use Agda. So you don't have to install anything on your computer. You can just use it. So that's perfect for us because we're not, I don't care if you learn how to really write Agda code for your own purposes. It's just something for that. So, next. Maybe it'll work anyway. I don't know. That's not good. I was literally working this morning. Oh, maybe. Hey, all right. I don't know if. I don't know. It's possible that multiple people can be editing this at once. I don't know, if you have a computer, if you want to try going to, if you click on the link for Agda, you go to top angles transfer slightly. Whatever. Bigger, a lot bigger. Is that good? Sammy, can you read that? Yes, so big enough? Okay. All right. So there's a whole bunch of kind of help text here and a comment where you can read it later, and we'll go over some of that kind of on the fly. Agda, in some ways, is pretty similar to Haskell. So when we start out, you're going to see things, syntax that looks kind of familiar. The way we define functions is familiar. The way we break down types of things. There'll be a few small differences, right? But we'll see that Agda has some features that go far beyond what Haskell has in certain ways. So, but let's start with some simple things. So let's define a type of booleans. Okay, so the data bool, and so in Haskell I would just say data bool where. In Agda, you have to say bool colon set. Basically, this is saying bool. I'm making a new thing called bool, and it's going to be a set, which is kind of Agda's word for type. I mean, so basically, this means we're making a new type. Okay, and then this is going to be the same. True is bool, and false is bool. Notice though, in Agda, it uses a single colon for has type, not a double colon. I think we talked about this the other day, right? Haskell's like the only language in this kind of family of languages that uses a double colon to mean has type and a single colon for colon. Okay, and then I can hit, I think it mentions this up in the help, but if you hit Control-C, Control-L, then it will load the file and type check it. Okay, and then Control-C, Control-L, and it's working for a little bit. And you can tell it succeeded because now everything has nice colors. Okay, so it type checked everything, and then sent some information to the editor about well, this is a variable, this is a data type, and it gives a nice color. Okay. And I think if there was an error, it would have said some kind of error down here. But let's try making an error on purpose, just to see what. So if I say boo instead of bool, it's not going to like that. Right, so we get an error. It says, you can't read that, but it says not in scope, boo. Did you mean bool? Yes, yes I did. So far, so good. Let's define not. So this is going to look very similar to Haskell, so not as type bool, arrow bool. But I'm going to do something fun. So I'm just going to say, well, I don't know how not's going to work yet. I'm not quite sure. So at least I can say, actually, is there even a way to, not B equals, so remember in Haskell you put an underscore if you're like not sure what goes there, and Haskell can tell you, oh, you know, like here's what type should go there. So Haskell got that idea from Agda, and Agda does it way better. Okay, so but in Agda you don't put an underscore, you put a question mark. Okay. So put question mark. Now watch what happens when I load it. I'm going to see Control C, Control L, and the question mark actually turns into this special thing called a hole. It's basically like, oh, I'm keeping track of the fact for you that like you haven't filled in some code here, and we'll see there's various ways of kind of interacting with them. And so down here it's hard to see, you can't tell, but it says like question mark 0 means hole number 0 has type bool. So it's telling us what type has to go there. So here's one cool thing I can do. I say, well, okay, how am I going to do this? I think I want a pattern match on B. That's probably a good way to write the not function, right? So of course I could go over here and edit it, and I could like write not true and not false. But Agda can do it for us. So I type B in the hole, and then I hit Control C, Control C. This is all listed in that list up there, so don't try to memorize. I mean, you'll memorize them after you do it for a while, but Control C is for case. C stands for case. We're doing case analysis, right? So I do that, and boom. It says, all right, here's the possible cases for like pattern matches on B, and then it'll just like fill in for us. And notice now we have two holes, right? So, okay, well, now you have to say what is not true and what is not false. So I can go here and I can say, all right, well, I'll just fill it in now. Not true is false. Let's put false in the hole, and then I think it's Control C, Control space. All the commands start with Control C, and then it's just like, you know. So Control C, Control space means I have filled in the hole. Please, you know, check that this is valid to go in this hole, and if so, then get rid of the hole and just, this is what I'm going to use. So if I do Control C, Control space, it says, yep, that's good. And, you know, let's put something else here on purpose just to see what it yells at us about if we, you know, what if I put like, bool? It doesn't make sense, because bool is a type, it's not a boolean. So if I do Control C, Control space, I get an error, right? It says, again, I don't know if I can make this bigger for you. I suspect I can make it bigger, but as soon as it gives me another error, it's going to make that smaller. Yeah, no, that's not helpful. All right, try that again. What? Oh my goodness. Okay, I get it. That is crazy. All right. That'll work. Yes. All right. Basically, it's saying like, you gave me something of type set, but I wanted something of type bool. Like you gave me a type, but I wanted a bool, and those aren't compatible. Right? That's basically how to read that. This thing means like not like compatible with, or not a subtype of, or something. So all right, let's go. Control C, Control space. All right, done. And I can, if I want, I can just like reload Control C, Control L, and yes, it's good with this. So I could now, if I do, I believe it is Control C, Control V, lets me evaluate some things. So if it just pops up a thing, it's like, okay, type in an expression, and then it'll evaluate it for us and tell us, so I can see if it's not true, and it'll say false. Right, so it works.
So that's the equivalent of loading like into GHCI?
Yeah, there is no equivalent to GHCI. Like Agda doesn't have a REPL thing. But if you just want to evaluate a certain expression, you can just type that command and it's kind of like a very poor man's GHCI. Here's an interesting thing. As we're going to see, a lot of times what you do with Agda is you don't actually run the programs. You just type check them. Because you're basically using it to encode some kind of theorem that you want to prove, and if it type checks, that means you proved it. And so you don't actually run it. You just care whether it type checks or not. It is possible to use Agda as an actual programming language. I think it has a backend that can output Haskell code, like it can translate the Agda into Haskell code, and then you could like compile that. There might be I think there's other ways. There used to be a JavaScript backend. I don't know. I'm not up on like, all of that, so I'm not sure, but in any case, a lot of times people don't actually use it to write real programs, they use it to like, prove things. In that case, you don't really care about a value. All right, any questions so far? Cool, straightforward, huh? Let's define natural numbers. So, this is in fact, of course all this is in the standard library, like the Agda standard library, but we're going to basically just define everything ourselves. So I could like say data nat, set. However, so what you'll find in Agda, like all the standard libraries of Agda, it has just like gone all in on using Unicode symbols for stuff. So like not just sticking to ASCII, like okay, any Unicode symbols are fair game. But this editor has you can if you type a backslash, there's various kind of shortcuts you can use to create certain Unicode characters. So we don't have to like copy paste them from somewhere. So for example, backslash B capital N makes that symbol, the like natural numbers symbol. Right, and it's got some examples up here, right? Or we could take like backslash alpha, it makes the Greek letter alpha, right? Whenever I use a fancy Unicode symbol, I'll always put a comment there saying like what the code is for typing it in. So, but it's to Agda, it's just a name. It just happens to use some Unicode characters. Doesn't care. So you can call things whatever you want. So, and of course, if you want an actual backslash, you just type backslash. Okay, well, what is a natural number? Well, we're going to make, let's say 0 is a natural number, and successor, right, and then often, I use like this arrow here, just like Haskell. However, that works fine, but also you'll often see, like if you write backslash TO, it makes this nice little Unicode arrow, which means the same thing, right? And it looks cool. So, okay, so we've seen this data type, a similar kind of definition before in Haskell, right? So values of type n include 0, and suck 0, and suck 0, etc. Okay. And I'm going to use a special, I think this is how it works. Basically, I'm telling it, hey, this definition that I made, I would like you to use this definition. Like, remember that this definition corresponds to your built-in idea of natural numbers. So now we can use, we can write, for example, 3. Like, actually type the character 3, and it'll translate that into suck 0. That just makes it more convenient for us. 3 instead of suck. So, for example, if I say, evaluate something, and I say, if I say suck 0, it actually prints out 2. It really is suck 0, but it's abbreviating it as 2 twice. Okay. Let's define addition. How about that? So here's how I'm going to do that. I could make a function called plus. But one neat thing about Agda that's different than Haskell. Well, Haskell lets you define operators too. Like I could say, I could define plus in Haskell like this. Agda uses a slightly different notation. So in Agda, you use underscores to show like where the arguments are going to go. And the crazy thing is, you can define like not just binary operators this way. But you could define like some crazy syntax like means like, well, anytime you see like a thing, and then a bracket, and then a thing, and then bracket caret, and then a thing, you know, that's like one operator. So you can define some cool notations and stuff this way, or make it look like math notation. We're probably not going to use that too much, but okay. So plus takes a natural number, and then a natural number returns a natural number. Okay, and then we'll say like x plus y equals question mark. We'll load that, and then we get a hole. All right. How do you think I should proceed? Any ideas? No ideas? And right now, I don't know anything about x and y. Right, so how do I kind of learn enough to figure out what their sum should be? This is what we did with when we defined not. Yeah.
Put x in the hole.
Okay. Put x in the hole and then what? Or just define it as x. Or do you mean?
Like just type x. Or can you type x and y in the hole? Like x comma y? Can you do that?
Well, maybe, but, so, what is your goal in typing using the hole?
To figure out, well, we know x is a natural number.
Right. And what do I know about natural numbers? How are natural numbers defined?
It's either 0 or successive.
Right, it's either 0 or successive, right? And I kind of need to know which one in order to figure out what their sum is. Like, they're just variables, I have no idea. Right. So do you want to, right, so we need a pattern match, right? So should we pattern match on x, on y, or both? What do you think? There's not a right answer here. There's no idea. Both. Okay. I think we can do this. So if I type x and y, and I just so Control C is for pattern matching. Yeah. So it's just like here's all the possibilities, right? It could be both 0, one could be 0 and be stuck. Okay, well now we just need to go through and fill in the answer in each case, right? So what's 0 plus 0? 0. Cool. What's 0 plus the successor of y? Successor of y. Easy. Okay, this is easy too. So x. What is successor of x plus successor of y? Suck of what? Let's call x. Oh, just x at this. I mean, I can. Like, that's accepted as a definition. I don't think that'll do what we want though. If I'm totally ignoring y, like, that's not going to be the sum of those two things. You're on the right track though. What is the sum of 1 plus x? I mean, successor really means 1 plus, right? So 1 plus x plus 1 plus y, what is that? Sammy? Of x plus y, yeah. I agree. We can try it out. If I say 2 plus 3, remember when I write the number 2, it really is translating that into like suck 0. And it prints 5. So it works. We can make this simpler actually. So this is, I want to write a different version of this that's going to make it a little easier to do things with it, improve things about it. So I think someone said we should pattern match on both, and it turns out that's kind of overkill. We can make a nice definition of addition that doesn't pattern match on both of them, but just pattern matches on one of them, typically x. So let's think about if I just pattern match on x, so I put x here, Control C, right? So it just has y. It didn't do anything with y, but we just looked at the different cases for x. Right, so, okay, 0 plus y, that's easy, that should be y. Okay, and what about successor of x plus y, what should that be? And just to emphasize, like, we don't need the parentheses, but that's where the parentheses go, right? So what should this be? Right, okay, so this. Okay, so first of all, does that make sense to y'all, just like algebraically? Like 1 plus x plus y is the same as 1 plus x plus y, of course. The question is, like, why is this an okay way to define plus? Like, for example, why won't this just, so it's recursive, right? This one was recursive too. This plus is just calling a plus. Why won't this get stuck in an infinite loop? Or in a recursion?
In both cases, you only don't know why. So if you're checking x, then it wouldn't get stuck in an infinite loop because all it doesn't know is y. So it could you're basically just one unknown variable in that case. So it's only having to check one equal to.
I don't think that's why, because like here, we successfully wrote plus where we were pattern matching on both, right? Because I could also I could say here's plus prime. And I could just say x plus y equals x plus y. And this is clearly not a good definition, right? This is just gonna, or even if I pattern match on x, I could say, whatever. I could just make it. So usually in Emacs, you hit Control W to delete a section of text. But since this is in my browser, Control W closes the tab. But thankfully, when I reopen the tab, I didn't lose anything. But so any other ideas? Why will this not get stuck in the recursion? Right. if the first argument is successor of something, we call plus again, but we're only calling it with x, right? Which this x is like, you know, if the argument was successor of x, now we're only calling it with x. So every time we call plus, we're taking off one suck off the front of x, right? And so it's getting smaller and smaller, and eventually it's going to get to 0, and then it'll stop. And in general, if you want to know whether you know, a recursive definition is going to always stop, you want to see if there's some argument that's getting smaller every time. There's more sophisticated ways to do it, but that's like the big secret. It turns out Agda is actually checking that for us. So this is another difference between Haskell and Agda. Haskell doesn't care. You can write whatever recursion the heck you want, and it's up to you to figure out whether it's going to stop or not. Okay? Agda, for reasons we'll talk about later, cares very much that every definition always stops. Basically, it's because if you could write infinite loops, then you could prove anything you want, and that would be not very useful. Then you could never be sure whether your proof was valid or not, or maybe you accidentally put some like infinite loop in there. And so if we try, if I change this to be like do something stupid, like, you know, let's say, right? I'll say, okay, to add x and y, you like add one more to x, and then you add those recursively. So now x is getting bigger every time we call plus, right? This is no good, right? This is going to blow up. But if I try to load this, Agda actually yelled at us, and it says termination checking failed, right? So it type checked. It had like all the types match up, but it could not prove that this function will always stop. And it says, yeah, you might want to look at this. This recursive call doesn't seem okay. Now, because of like, we've heard of the halting problem, right? How it's actually impossible to check for sure and say whether a program is going to stop or not. So Agda can't tell us 100% for sure. It's basically doing a kind of conservative analysis. So if it says okay, then for sure, yes, it will terminate. So it's kind of using some criteria, and if it can show certain things, then yes, it knows for sure it will terminate and it's okay. If it gives you this error, it doesn't necessarily mean it will for sure go into a loop. It just means it couldn't show that it will always stop. And so sometimes it's kind of annoying that you have a definition and you're like, no, I know for sure this is okay, but Agda's just not able to see it, and I have to rewrite it in some way to get it to accept it. So that's kind of the price we pay for having a language that lets us like be absolutely sure about our proofs. So all right, let's put this back. Okay, so it accepts this, and we already tried it out. So let's, I'll just delete this right here. So you know, and when you're doing some homework, doing Agda stuff, you know, you want to think about this. Like, it's easy to just be like, okay, pattern match and everything in sight. It's just pattern, but then you end up with like, you know, 50 cases to prove, and probably a lot of them are redundant, right? So you want to pattern match on what you need to, but not any more than that. Obviously, we have to do some pattern matching here because otherwise we have no idea how to proceed at all. But it turns out we don't need one. All right. Cool. So that, I think, that's all I wanted to say about natural numbers. All right. So far, I mean, yeah, we've seen some interesting differences that Agda has with Haskell, and some kind of things it can do that Haskell can't do. But the actual code we've written, like all of this code we could have written exactly in Haskell, just with slight syntax differences, right? So I want to next show you. Oops. So I want to to start making precise this idea that we can actually, you know, encode proofs of things in Agda. And, right, this is leaning very heavily on this idea that we talked about the other day, where the Curry-Howard isomorphism, right, where propositions and types are identified, and proofs of those propositions correspond to programs that have those types. And so basically, Agda takes that and runs with it by, you know, having a very sophisticated type system corresponding to a very sophisticated language for writing down propositions. So I'm going to start with something simple. We're going to write down a type of proofs that a number is even. So we're going to kind of write down what does it mean for a number to be even, and like how would you prove that a number is even. Okay. So I'm going to write down a type for proofs of evenness. And here's the idea. What does it mean for a number to be even? Or how would you prove it? How would you... And of course you could say, well, just look at the last digit. And if it's even, well, okay. Or you could say, well, it's... there's multiple ways you could answer this question, right? You could say, if there's some number that is 2 times that number. And like I'm teaching discrete right now, that's kind of how we define it discrete. We're going to define it in a slightly different way here. We're going to say, first of all, 0 is even. And the second of all, we're going to say, if n is even, then n plus 2 is even. And I claim that we could take this for natural numbers. I'm not talking about negative things. For natural numbers, we could take this as a definition of what it means to be even, right? Because like, well, 0 is even, so because 0 is even, then this rule implies that 2 is even. And then since 2 is even, we can apply this rule again, that implies that 4 is even, right? So any number we could kind of get to it by starting with this rule and then using this rule a bunch of times. Okay. So I'm going to write down those rules, but kind of as a data type in Agda. So I'm going to call this data even. And, you know, I could just say even is a type. However, it's supposed to be like about a certain number. So if I have something of this type, it's supposed to be a proof that, you know, 10 is even, or a proof that 12 is even. And I need to know what number it's talking about. So actually, let's do this. We're just going to proceed. We'll come back and talk about this more later. There's a lot to say about what exactly we're doing here. But I think if I talked too much about it, it would just go over your head at this point. So we're just going to keep going. But the point is, like, even is kind of parameterized by a number. Well, we've got these 2 rules. Each rule is going to correspond to a constructor. Okay, so I'll call this ZE for 0 is even. And the type of ZE is even 0. Right, because we said that even kind of takes an argument, which is a natural number. And so the way to read this is ZE is a proof that 0 is even. Or we could read it as ZE is a constructor, you know, that gives you something of type even 0. So ZE has type 0, i.e. proof that 0 is even, right? Or it's just our way of encoding this rule from above. Okay, and I'll call this ZS for no, not ZS, SE for successor even. I mean, it's really, I guess I'll call it SSE for successor of successor. Now, how do I write this? So, notice that like this rule is about a specific number 0. This rule actually applies to any n. Okay, so actually I need to kind of take what n I'm talking about as an extra parameter. If I just wrote like, well, maybe I'll start with this. So if then, right, if then statement is encoded as a function, right? It says, okay, if you give me a proof of this, then I will give you a proof of this. So we could say, well, if n is even n, then even of successor of successor of n. Yeah, but Agda's not going to accept this. It's not going to like it because it's like, I don't know what n is. You haven't defined n. Okay, if I try to load it, it's going to yell at me and says not in scope n. So I need to take a natural number as an argument so that it knows like which n I'm talking about. So I could write this. The problem is n is, I still haven't defined n. And so I actually just say, yeah, the first argument is going to be a natural number, and it should have the name n. This is how you can kind of name an argument. Right, so this is what type the argument has, and this is its name. And then I can use it over here. So, we can try using this in a second. Let me just pause and say like how strange this is, that right, I take a first argument, which is a natural number, and then the second argument is something of type even n. But this n is a number, and it's showing up inside the type of something. Right, so in Haskell, this doesn't happen. Right, in Haskell, there's this pretty clean separation between I've got values and I've got types. And like, they never get mixed. Right? You can't have like the number 3 in the type of something, right? But in Agda is what's called a dependently typed programming language, which essentially means you can have values show up inside of types. There's actually no distinction between values and types at all. There's just values, and some values classify other values. So some values we think of as types, and they just like so. Agda values and show up in types. In fact, there are really only values. Some values classify other values. For example, right, 3 has type natural number, but natural number is a type, and it has type set. We've seen that before, right? When we said like data bool colon set, we were really saying, I'm defining a thing called bool, and here's what type it is. It's set. You could ask what type set has, and it has type like set 1, which has type set 2, and so on. But, okay. Again, we'll go more into this. Don't worry too much right now about like whether what I'm saying all makes sense. You can just kind of get the general gist of it, and you know, we'll continue building on this, and hopefully it'll you know, we'll do more examples. We'll come back and talk about it more specifically, but for right now, let's just see how we can use this. So, first of all, I just want to like one more time kind of like pronounce what we've written here and just make sure everyone believes at least that it corresponds to these rules. So this says, how do you make something of type even n? Well, there's two ways. You can either say ZE, and that makes something of type even 0. And we think of that as a proof, encoding our idea, our rule, that 0 is even. Or, this says, all right, you can say SSE, and it takes two things. It takes two arguments. The first is a natural number, and the second is a proof that that natural number is even. And if you give it those two things, that whole thing will together count as a proof that n plus 2 is even. And you know, and also just emphasize, we just made this up. Like, Agda doesn't know or care what even means. have defined this any way we want. It's up to us to kind of convince ourselves that this definition corresponds to our idea of what evenness means. All right, but let's prove that 6 is even. So 6 even will have type even 6. Okay, and basically, if I can define this in a way that Agda accepts, that basically means I have proved that 6 is even, at least according to our rules. Well, how do I do this? There's only 2 possible ways to make something of type even 6, right? ZE or SSE. ZE definitely doesn't work, because that's not the right type. That has type even 0, and I want even 6. So I can't use that one, so I guess I better use SSE, right? So SSE, and I need to give it 2 arguments, right? I need to give it a number and a proof that that number is even. So what number should I give it? Sammy? 4. Why 4? Right. Right. SSE says, look, you give me a number, and I will build for you a proof that 2 more than that number is even. So since we want to prove that 6 is even, we should give it the number 4. Right? And then we'll also have to give it a proof that 4 is even, but we'll get to that in a minute. I can just fill in 4 here, and then I'm going to put a question mark. So this is a nice thing, right? When you're filling in a hole, you don't have to fill it in completely. You can fill it in partially and leave some other holes, and then if I say Control C, Control space, it's like, sure, that part you put in there makes sense, and now you've got this part left to do. Okay? And now it's telling me, yeah, you've still got to prove that 4 is even. Okay? How would I prove that 4 is even, what do you think? What was that?
Sure that number again? To 2.
Yeah, so I have to use SSE again. 2. Oh, I didn't put a question mark there. It was yelling at me because it's like, I didn't give it another argument, and so it was still, it didn't have the right type. Okay, and then, now I have to prove that 2 is even. We use SSE again. With 0, question mark. Okay, and then finally I have to prove that 0 is even. The way I can do that is I use ZE. So now I can say ZE, and done, proved. Here's a cool thing. So we kind of know how this would go to prove that ABZ. There's a couple interesting things I can do. One thing I could do, Control C, Control R, so I think R stands for refine, where basically Agda's like, if Agda can figure out there's kind of only one thing that could possibly work, it'll fill it in partially for you. So, you know, Agda can look at this, like do the reasoning that we did and say, well look, you want even 8. There's only 2 ways to make even things. One is ZE, but that doesn't have the right type, so that can't be it. So if it's going to work at all, it has to be this one. So we can just like fill in this for us and like put some holes. So if I say Control C, Control R, it says, yeah, it's got to be this, and now you've got 2 things left that you got to do. And then we can go through and fill in, you know, 6 has to go here, and then here. Well, maybe I can do Control C, Control R again. Look at this, right? It gets even better. In this particular case, like, this is pretty mechanical, right? Like, it's not that hard to figure out how to make this work. So if I do Control C, Control A for auto, it figures out the whole proof for us. Because we've encoded so much structure in kind of like in the types, it can kind of just do kind of an automatic search and say, well, this doesn't work, this doesn't work, this doesn't work, type up. This is the only thing that could possibly have the right type. So I'll fill that in. As long as I can find something that has the right type, it'll fill it in for us. So it's basically, this makes it that Agda is not only a proof checker, it's also a proof assistant. Like, it can actually, like, help us do boring parts of our proofs, right? I mean, it can't, like, you know, if you do more complicated things, it can't necessarily figure out how to prove it for you, but in many cases, it can, like, be like, oh, this is a boring case, just, like, pattern match on this and now do auto, and it's just like, yeah, I filled it in for you. Here.
Did it use the word zero because that's how you had to define the natural numbers?
I don't know why it used the word zero instead of the number zero, because, I mean, they're equivalent. Because we told it that our nat thing is, like, corresponds to the built-in natural numbers. Those are the same. So I don't know why it chose to use the word zero. It's significant. Any other questions? Cool. Well, I will figure out how to, like, post this not only as the actual, like, the text of the file, but, like, see if I can post, like, maybe a link to this thing on Agda. I don't know, I'll figure out a way to post it. So I mean, you should be able to play around with it yourself, not just, like, reading text. And you should feel free to do that. You know, of course, we will eventually have, we'll have an assignment where you do this, but you can start playing with it.